All right, moving on from percentiles, let's talk about z-scores for a little bit. So all a z-score is, it's the number of standard deviations a value is away from the mean. So standard deviation just again tells us how far something is away from the mean, gives us a standard unit of measurement for that. And the z-score says, well, how many of those deviations are we away from the mean? So a small z-score would mean we're very close to the mean, and a larger z-score would mean we are much further away from the mean. And the formula for our z-score, it's really simple. All we're doing is taking our entry x, subtracting away the mean, and then dividing by our standard deviation. So let's say z is equal to, we've got our data entry, we're seeing how far away it is from the mean just by subtracting it to find the difference, and then we're taking that difference and dividing it by our standard deviation to see how many total standard deviations we are away from the mean. It's a really nice, concise formula there. And what do we know if a z-score is positive? Well, if we get a positive value, that means the value is above the mean. If we have a negative value, that means our value is going to be below the mean, less than the mean. And that's just referring back to this formula. If x here is going to be smaller than our mean, when we take the difference, we're going to get a negative number, which is going to give us that negative z-score. So smaller than the mean, we'll get that negative z-score there. Same thing with our positive one. If x is bigger than our mean, this difference is going to result in a positive number, so we'll get that positive z-score. And if the value is equal to 0, that means this difference right here is going to be 0 up top in our numerator, meaning that the value is equal to the mean. Let's take a couple of looks at some z-score examples. So we're going to say John got a 31 on the ACT, and assume that the ACT is normally distributed with a mean of 21 and a standard deviation of 4.7. Mary got a 1260 on her SATs, and let's assume that the SAT score is also normally distributed with a mean of 1016 and a standard deviation of 111. Who scored better? So we can use our z-score to see, even though they took different tests, how they compared to the general population and see who scored a little bit better on their test. So let's do John first, just because he came in the problem first. We're going to call his z-score z1. That's going to equal, I'll just do everything with a sub 1 here, just so we can keep these two separate. Our x1 minus our mu1 minus our sigma 1. And let's just plug in the values for all of these. So his score, John got a 31. The average for the ACTs is a 21, and then the standard deviation is a 4.7. So once you plug all that into your calculator, we're going to get a 2.13. Now let's take a look at Mary. So Mary, we'll call Z2 is equal to x2 minus mu2 all over sigma 2. And Mary got a 1260. We'll subtract the mean there of 1016. And we're putting that all over a standard deviation of 111. Once we plug this into our calculator, we're going to get 2.20. And with our z-scores, I'm going to ask that you always take these to 2 decimals here. Later on, we'll take a look at finding these in tables, and tables always use that 2 decimals, so that's a good place to round to in any case that you calculate these. But back to this problem, so we've got our z1 is 2.13 and our z2 is 2.20. Well, this is a little bit bigger than this one, so we know that in comparison to the mean, Mary scored a little bit higher away from her average score than John did on his ACTs. So Mary's score in comparison was a little bit better. All right, let's do 3 more examples here for our z-scores, and we'll wrap up the video. So we can say that the average lifespan of a washing machine is 12 years with a standard deviation of 1.5 years. The average lifespan of a dryer is 15 years with a standard deviation of 2 years. Suppose that you had your washer and dryer for 14 years and 16 years respectively. Which one is older to its relative other appliances of the same type? Whenever you see this respectively here in math, that means we're going to take the 2 numbers that appeared before it, and they correspond in the same exact order of the terms earlier in our sentence. So if we had 14 and 16 respectively, that means our 14 correlates with our washer because that came before our 16, and our 16 comes with our dryer. So I know that messes up a couple of students now and again, but that's all that respectively means. So let's take what we know again, and I'm going to do a Z1 and a Z2 just to keep these 2 separate. So we'll have Z1, let's just say that's for our washer. We'll plug in everything that we do know. We've got x1 minus mu1 all over sigma 1. We're told all of these values. Our x1 is going to be our 14 years. Or x1 is our 16 years. So that's the age of our washer. Then we're going to subtract our mu1, which we are told is our 12 years. And then we're putting that all over our sigma 1, which is 1.5. And I'm just going to write that off to the side here because that got a little sloppy. x1 is equal to, oh no, I was right beforehand. x1 is equal to 14. Our mu1 is equal to 12. And our sigma 1 is equal to 1.5. So again, let's just scratch that out. That's our 14 there. Do that in a different color again. And once we plug all of that in to our calculators, we can see we got a Z1 is equal to 1.33. Now let's do our dryer. And this time I'm just going to write these out so I can keep these clear. We've got our mu2 is equal to 15. Our sigma 2 is equal to 2. And then our sample here next to is equal to 16. So now if we're plugging all of these in for our Z2, we're going to get 16 minus 15 all over 0.5, 0.5, or all over 2, which is going to equal 0.5. So our Z2 is equal to 0.5 here. So our Z-score for our washer was 1.33. For our dryer, it's 0.5. So that means our washer is much higher or much more above the mean than our dryer is compared to the same type of appliances. So if we're talking about which is older, we can say our washer, even though it's only 14 years old in terms of the average washer age length or lifespan, our washer is older in comparison here. So our washer is more likely to break soon in this case. So let's say, do it in that green color. The washer is older. I'll put the older back in quotes. Older relative to its appliance type. All right, 2 more examples here. Jaden just got his last math test back. Mr. Sneeringer didn't give him his actual percentage, but rather his z-score of -3. If Jaden knows that the mean was 72 and the standard deviation was 6, what did he earn on his test? So right off the bat, I see a z-score of a negative number. So that says he definitely scored below the mean. So let's figure out exactly how far below the average that Jaden scored. So I'll copy that formula down here again. We've got our z is equal to x minus mu all over sigma. And let's just plug in what we do know and solve for what we don't know. So we're told our z-score is -3. Well, we don't know Jaden's test score. That's his x. So we're going to leave that in terms of x for now. And then we're going to subtract the mean, which was 72. And then that's all over our standard deviation of 6. So now we just have a nice simple equation here that we can solve. First thing that I'm going to do is multiply by 6 on both sides, times 6, times 6, and we'll get -18 is equal to x minus 72, and we're just going to add that 72 to both sides. And we can say x is equal to 54. So Jaden scored a 54% on his test. And again, that's below the average because of that negative z-score there. And that's quite a bit below average too. So if you see a larger negative z-score there, that means we scored much further away from the average than, let's say, his z-score was -1. Now let's take a look at this last example. So Dante took the same test as Jaden, and his z-score was 1.5. What did he earn on the test? So now we've got a positive number, and that means he's going to have scored above the average here. It's not quite as big in terms of its absolute value as that -3. So it's not going to be as far away from that mean of 72, but it will be above it because we have that positive z-score. And let's just take everything that we do know again and plug that into our z-score formula. So we've got our z-score value of 1.5 now this time, and that's equal to our unknown x over this, subtracting that same average of 72 all over our sigma of 6, our standard deviation. And then we're just going to solve this the same way here. Multiply 6 on both sides, times 6, times 6, and we'll get 9.6 is equal to x minus 72. Now we're going to add that 72 again. We'll get 81.6 is equal to x. So Dante got an 81.6%. So it's pretty good, actually. All right, that wraps it up with our z-score stuff, and I'm going to call it an end to our video there for now. I'll see you all in the next lesson. I hope everybody's been doing well. But I'll see you soon.